Good morning. Yeah, so we're starting on the next chapter. And like I said, what's sort of the second last chapter, next is deflection of beams, and then buckling. We will be doing, but it's not that much in depth. And the reason why I say that, obviously I've set the final and I'm roughly aware what's coming in. So I'll just obviously, so I won't waste too much time on particular stuff. And obviously the next two chapters will be coming in your next class test, which is I think on the 18th of October. So yeah. Okay. Like I said, I did finish marking. You hit your marks later today. I hear you guys, are you guys writing their work, or do you guys have an assignment? You?
No, sir, we are writing, and we are writing on Thursday.
On campus?
On campus.
You know what? Guys,
you can see my leave scripts here by Mr. Kane.
Yeah, but I'm not going to be that side. I run a bit of a tight schedule. I'm on Belleville. But thanks for that idea. Yeah, you know what? Thursday. I must really just see. But let's give it just talk to me, please. Man, I know you're so busy. Later on. What I wanted to say was, you see, guys, my concern, not my concern, right? So I look at the marks, and what tends to happen is that I can't provide any intervention to assist you guys. Really, our schedule is so tight, and obviously, I have to mark 1,000 billion things here, and it's really not working for us. So somehow I want to find a way, maybe to create some kind of assignment. And the reason why I'm doing this is because I want you guys to, well, if you guys are back, the thing is, the real thing is that I want people to work hard. That is the bottom line. Some people are not pulling up their socks. So when I do these things, sometimes like you do it for the wrong people, and then people still end up failing the final. And what I'm telling you, I want to do it so the point that people can actually improve their marks and do better, not just copy from the next person. You sit down and burn through the stuff. And so I would really like to have some kind of intervention, or some assignment or something like that. But the problem is that the only time to be there to be during your exam week. So that's my real issue. There's no other way on why this course is structured. So, but anyway, I'll see. I can't think of the future. I mean, I love week to week here, with the amount of work I have. But I want to get all the first tests done, and that's my next aim, and take it from the second test. So I just thought I'd mention it. Anyway, guys, we are chapter 11. I'll show my textbook. I have a textbook here. But obviously, when I post the marks, the reason why I need to complete, like when I complete the cycle of stuff, I have to scan in the class test, scan in the memo of the class test, and obviously the class test as well. Yeah, so that is what I want to do. So just put the marks up and do it afterwards. So I know I'm done with that task. Yeah, chapter 11. Bit of a small chapter, can be a bit tricky, I guess, but if you just kind of pay attention, you'll be fine. And again, guys, you know, like I always say, just the lectures are really key. I'm not trying to trick. I never try to trick anyone. It's just never the case. Now I'm saying this because we get into time and focus on what I'm saying in the lectures. Practice what I tell you to practice. You'll be more than fine. And in the, well, obviously in the exam, that's going to be on you or the test. So yeah, you know, this is not difficult. You just have to really pay attention. No, I don't trick people. I don't know. It's like you guys think I trick people. It's not. Straightforward questions. I mean, my highest mark was 80%. That's pretty dope for the subject. So that means that's something good. Yeah, no one could solve question 2, but yeah, well, it was expected. I had a feeling. Yeah, no, it's not tricky, you know. Like, I think maybe for you, Alex, and again, before I start, I man, I can't even remember all the marks. But what I'm saying is that it's this thing of studying from the textbook, and the textbook has specific. When I am using the textbook, but you know, like you need to just follow me, and you'll be okay. You know, textbook can be a bit unnecessary sometimes. But anyway, let's just move on. So shear stress in beams, right? Second last chapter. Next week we do deflection in beams. We'll be closing that off. Some people find it rough. I actually enjoy the next chapter. In fact, for the next few chapters of strengths, I'm enjoying all the chapters. I just have to put lectures for them. But yeah, hope you guys enjoy it too. I think it's going to be too complicated, so don't worry. So let's talk to this. So in chapter 6, which is the shear force in bending moment chapter, we saw externally applied loads produce internal shear force and bending moments in the cross section of a beam, right? That's the purpose of chapter 6. Then the bending moments cause direct stress distribution to the beam, and now we will determine the corresponding magnitude and distributions of shear stress. So chapter 6 was the initial platform. You know, obviously you do this abstract concept of a shear force in bending moment in a beam, but now what we actually did in the previous chapter, we had a look at bending particularly within beams, and also we you know, we looked at how to find the stress. Obviously, that is what you want. You want to see if can the beam withstand a specific amount of load, and we actually did that, find the maximum bending moment. But what about the shear? So now we're going to unpack the so-called idea of shear within a beam. So this is also important. They're saying the effect of shear is quite small compared to bending stresses. Obviously, this depends on the length of the beam. I didn't mention when the beam is very long, it's most definitely going to fail by bending, but if it's a very short, stubby beam, it's more likely going to fail of shear. But obviously, there are reasons why we have to analyze shear stress, because obviously it is a force acting on the beam. But what is its significance? So I say, however, in some cases, desirable to consider its effects. In most cases, beams are designed for bending and check for shear stress. I think I kind of said that now. So what they say here is that the magnitude of shear stress becomes important when designing beams in bending that are thick or short. So I mentioned stubby, right? Beams and wall failing shear while bending. To calculate the transverse shear stresses, we use applied shear force, which can be obtained from the shear force and bending moment diagram. The first moment of area and thickness of the region of interest, and the second moment of area of the entire structure. Right? So that is what we will be touching on. So before we actually talk about this man has been doing research. I hope you guys watch their videos on the Efficient Engineer. It's one of my favorite YouTube channels. There's literally a video for all of my sections. I wanted to thank him or send him an email at least. And let's move on. So yeah, I'll get that slide must be shifted, and which I'll shift. But anyway, right? So when we're looking at a beam being loaded, so let me just quickly copy and paste the beam here, just for my own sanity. I must tell you, sometimes you guys, you really, you make me feel sorry for you, man. Amount of work you guys have, but anyway, fuck. Sorry for. Where is this? I'm just gonna find a random beam. Just bear with me. Oh man, now it's sticking. I'm not getting what I want here. I'm just gonna choose a beam here. Let me just go to the end. Yeah, this is just some makeup. No, don't worry too much. Just a picture of a beam. Just want to paste it because, like, when I talk about it, you guys have some image in your mind of what I'm talking about. Okay, I've got a beam here. Yeah, okay, cool. I'll just take this. Just take this beam here. Cool. And I'll just quickly paste it, right? So like that. So yeah. So anyway, there's a beam. You get the idea. And thank you for your patience there. And there are two kinds of shear force we'll be looking at. So obviously the first one is the transverse shear force. And the transverse shear force is essentially what they're saying is the vertical loads on a horizontal beam, which causes the vertical shear. Obviously, it's from the website over there. That's the website I was talking about. I'll just paste it just now. And what that UDL and that so-called point load of 40 kilonewtons on point C, it wants the beam to shear, right? And basically, he has two magnets. This guy's two magnets over here, illustrating what the shear force is. So obviously, we have experience with a vertical shear force. This is not new to us. However, what happens is with the vertical shear force, and there's something important. Now what they say here is that, well, it's titled longitudinal shear and bending, but it says in addition to transverse shear force, a longitudinal shear force also exists within the beam. Evidence of this longitudinal shear force is parallel to the beam axis is shown below. So what we're looking at here, and this is what it says. So imagine imagine some planks laid on top of one of each other, and obviously what happens now, and that's it, figure A. We apply a load, it begins to bend, and what we're going to find is that in B, there's some sliding happening within the surfaces between the surfaces of each plank. So they're saying apply a center concentrated load to the planks at midspan will cause to bend, shown in figure 10.1b. Due to bending, the underside of each plank will stretch and the top side will shorten. Obviously, we're familiar with that. They're saying it follows that there must be some relative sliding between the surfaces in contact. Very simple way of putting it. That's what it basically is. And what they're saying is that because of this load, because of obviously the way probably a material structure, we've got this horizontal counterparts happening. The other using example, the same thing, and they're saying obviously if planks are glued together, there's no slippage occurs, and basically the glue which keeps the beams together induces a shear stress. So it sounds a bit of a vague concept, and I can agree. However, it is there's a real reason why it's there, and if you do more advanced things, it actually becomes more obvious. And so I'm making aware this transverse shear basically is longitudinal shear, and based on that, there's a relationship between the two of them. And what they basically say is that the transverse and longitudinal shear forces produce stresses called the vertical and horizontal shear stresses. So what tends to happen, you're taking a small element, you load the beam up here, you find there are shear stresses on all sides of the beam, the vertical ones and the horizontal ones. So this is a new revelation, obviously, and they're saying these stresses are shown on a small part of the beam figure above. At any particular point in the beam, the horizontal stresses is equal to the vertical. So fortunately, they have the same magnitude, so we are able to compute them. So just be aware that even though we want the beam to actually what's what I'm looking for, it's going to fail vertically, or this vertical shear was transverse. There's also longitudinal ones. Now I was going to touch on that one. Okay, this is going to continue there. Okay, and this is just basically continue on the same thing. I've referenced the thing over there. I'm going to touch on maybe one or two examples I found last night, so I'm excited to just maybe use one or two there, and basically just proving that the shear force is the same. So be aware there's a vertical and horizontal shear force happening. So in keeping with the previous slide, and this is where this was supposed to be, I actually just added the slides hence the jump around. So this is touching on the same thing and basically just telling you that there are, again, there is this so-called longitudinal shear forces within the beam. And it's important to note here, this is important in design of connections, say between a concrete slab and the flange of an iron steel beam, where connections, usually steel studs or bolts, are subjected to horizontal shear. Why this is particularly important is more for the joints, the analysis we are doing. Because if you actually done some analysis, which you're supposed to do in connection design, which we look at rivets, we look at welding joints, and we look at bolts, and there's a whole analysis, essential materials analysis based on that. So this horizontal shear force, what we're going to compute, is actually one of the main criteria to look at that. So I didn't touch this on the previous lecture, but there was ways a beam can fail, and there are in fact 6 different ways, 6 primary ways a beam can fail, or they can be in a combination. And one would be web wrinkling, and one would be fastener failure. So both of these cases, if you look at them, as you can see, the web wrinkling failure, you can see that that's due to a horizontal shear. You can pick up on the direction of that line, the fracture line, and the fastener failure is exactly what I said. There is going to be horizontal shear forces. So obviously, say a robot's holding the cover plates to a W beam, or whatever they call it, W beam, or failing shear, right? And that obviously is induced by the load on top, which is this now the longitudinal shear force you're talking about. So once again, I'm always over the top. Dosky doesn't tell you this, so I'm making you. It probably does in the most concise words possible, but I'm just making you aware that's what we're really looking at. Okay, that's just some I-beams with bolts and stuff there, just for show. Okay, so now we're going to get to the nitty-gritty of this chapter. What's important is we're going to be looking, like I said, we're going to compute some shear stress distributions across specific lengths of beam. What's important here is that you must also be aware that each beam has its own kind of shear stress distribution or east cross section. So if you look at the rectangle cross section, you can see it has this nice parabolic shape. You look at an I-beam, it goes and then abruptly increases at the end of the, is it called the flange, and then it's all symmetrical. If you look at a triangle, it's something similar. If you look at a circle, it looks somewhat similar to all the others. Now, I just want to ask you something before I move on here. So I'm just going to use the slide, and this is obviously a T-beam. I've got basically all the other beams which I want to talk about. The reason why. So remember, let me just use the I-beam. Do you remember in strength of materials 2? I'm just going to ask you, do you remember the relationship between, if you had a shear force and bending moment diagram? What is the relationship between the shear force and bending? Think of the shear force and bending moment diagram and tell me some relationships about it. In terms of like, if you had let's say you had a graph or something. Maybe I can find a basic one here. You can tell me. Can you guys hear me? Bill says you can't hear anything. Otherwise, refresh. Am I audible, guys?
Yes, sir.
Okay, thank you. Fantastic. Okay, anyway, so you remember in the shear force, when the shear force was 0, no man, what is just, what's going on here? This means my tablet is not again. Flip, man. Okay. I need to. So when shear force is 0, what is the bending moment? Let me download this drivers. You guys remember what was the bending moment? I'll give you a minute to think about that.
Brent just tuned now.
Excuse me?
Brent just said now that it when the shear force is 0, the bending moment is the maximum.
Is maximum. Oh, I didn't actually see it here. Fantastic. So do you remember when we did the distribution of a I-beam? Do you remember how it looked like? So assuming we're applying a load here, obviously, the standard, how did it look like? You guys remember?
It looked like a trapezium, didn't it? Or like, not like a Z. It looked like a.
Yeah, there we go. That helps. Yeah. So also, I think what I'm looking for is, its top is being compressed, right? Those the tensile top is being compressed. So let's just say like a line like this. Oh man, yeah, you can see my graphics tablet's like my pen is here, but yeah. Anyway, so I had a so-called as these trapezium shape or right angle triangles. Some things a trapezium as well. Yeah. And what is important to note is that you can see at the top the flanges carry where the shear force was 0. We found out that the bending moment is a maximum. It makes sense. And at the bottom at the neutral axis, so basically there's no bending occurs, define a maximum shear force. So that's a new revelation. And what's important about I-beam, although it's designed, is that the flanges, you might get a free 2 bonus mark questions, that the flanges carry all the bending and basically the web carries all the shear. That's how they designed it. Obviously for this it'll be completely different. We know we had a different case over here, and an info beam like this. So that's just a new revelation on what, a so-called of the shear stress distribution. I want to make you aware that you will be required to compute the distribution for an I-beam, right? So you should really put a lot of emphasis on mastering that. Questions can easily go for around maybe 10 marks. So I'm just installing my drivers here from the graphics tablet. Okay. I did mention that the shear stress distribution, the beam depends on geometry. Yeah, we had to look at a few of those anyway. Okay, so finally, so what's missing here? It's just the derivation of this, and I don't want to spend too much time on that. It is in a note which I've posted, and it's arguably self-explanatory. Obviously, you don't have to know all the how it's actually done. There's a few notes I've posted, and I'll just copy the thing here. It'll look like this. If someone can find this textbook, really, I will be eternally grateful. It's like I really don't know what textbook it is. I'll just quickly duplicate this and paste it here. So it's not really of importance, but it's one of the notes there. And what it is doing here is basically showing you. Sorry, man. It's basically showing you how the formula which I'll be talking about now has basically been derived, right? So you can have a look at that. And so the main model we'll be looking at is this guy over here. I'm sure it's in your textbook, you've seen it. And it's going to be so it's basically your shear stress. To find the magnitude of it, it's going to be V, which is the maximum shear force, A, which is your area of the particular section you're looking at, Y bar is also to respect to that particular section we're looking at. And you understand what I mean by the particular section, and we divide it by the second amount of area, the total second amount of area of the object times the breadth of the object, right? So we're going to look at basic shapes, so at least, if you can master those, you should be okay. They're saying, so in the normal other types of, what's the word I'm looking for? Man, I'm getting a headache of this now. Just bear with me, sorry. Okay, it does work now. Let me just quickly see. Yeah, it works, okay. Is that they have AY as Q, however we just use it as AY. So Q, AY, but this is the one we use here, okay? And it's just, this is just a small note here, but they say determining Q or AY is more challenging part of these problems. This is something that requires a lot of practice, and I agree, a lot of people get confused on how to take that particular thing. Obviously, I'll try to break it down as best as I can so that you understand, and of course delineating the sections. Okay, so we can finally start on the first example. So if you do want to follow along with your notes, maybe this is the first note in the additional. It's called additional notes on shear stress beam in Beams 2. You can download it. You can actually have a look through it. I love this note really. I think it even has very nice questions here. But I really want this textbook though. Someone can find it for me. I'll be eternally grateful. I've been looking for this textbook. So you can just get that note ready, and we can actually start solving the problem. So we're going to actually start solving now, and I think getting on. So I hope you guys got the basic concept, obviously. Was there any questions? I don't really expect questions, but yeah, you know, expect questions once we start solving. Any questions, students? No. You guys waiting for me to talk. So mine all on havoc. I'm not saying anything. You guys still there? Hey. Oh. Guys, please, man, you're killing me here. Okay, so I'm going to just share my whiteboard now. Well, actually, what I should do now is go to the website I was talking about. And maybe I should solve a problem there. Okay, so let me just quickly see. Yeah, let me just quickly let me warm up with this problem. So this is on the website I put up. Okay, so just bear with me before I actually solve this problem. So I'm gonna just close in and start here. Okay, cool. So I'm gonna solve it. I'm gonna obviously solve it with you, and then like not from first principles, but you know what I mean. And then I will go back into this one just to get you guys warmed up, basically, to see if you guys get the concept. Okay, I'm assuming you guys can see this. Okay, guys, your rectangular cross section in an I-beam is of utmost importance for this chapter. So I highly recommend you take this particular part seriously. So what they want here, so this is just a warm up. You're going to do this actual distribution thing. So I just you know, it's just very good to me sometimes. You know, all the time, I guess. Sorry. So anyway, we have this beam, and they give us a vertical shear force of 10 kilonewtons, right? So they give you Vmax, right? So normally they normally will give you Vmax, or I'll request you to work out Vmax, and I'll demonstrate to you those times when we have to work that out. And obviously we have I here, and I is normally we have to work out I, but fortunately they've given it to us. So I'm not sure that's times 10 to the 8 millimeters for, right? Okay. So I'm not sure in our SI units, what is that? Can someone just work that in meters for me? So this is like a teaser of some sort, you know, of how this works. So our formula is like this over IB. Yeah. Okay. So just can I just get the I beam? So obviously the I is worked out the same way as before. We know the BD. We can actually work it out now. Maybe let's just work it out. Let me just get my calculator quickly. Where is my calculator's in the it's in the car. Okay. So I'm just work out my second one. It should be the same. I'm just using my Casio here on the computer. So it's going to be 0.1 times 0.25 cubed divided by 12. So we all can do that. Obviously, depending on the XX, yeah, so it's 130. Point, what's it? No, man, it just went away now.
L to the power minus 4.
Yeah, 130 how much? I was listening to you now, you just, yeah, not 4, man. I want to times 10 to the power 6. So it's 130.208, yeah, okay. Okay, so yeah, anyway, it's the same thing. So what we're going to do over here, so they've given it the same thing. So the question is find the vertical shear force at AA, right? So yeah, thank you, got it. So at AA, what AA is basically 50 millimeters up from. You don't worry, the next example is going to be a lot easier because I'm doing this one. So that's 50 millimeters away from the neutral axis, right? So how do we compute this, right? So what do they expect of us? So this is this thing they talk about. Q is a bit tricky for some people, but obviously because I'm the best, I've managed to make this work for you guys. So just this is why I'm breaking a small concept in a small piece so once you board it up, you're going to get more comfortable with it. Anyway, don't talk too much. So the first thing we're going to do, so they're saying 50 millimeters away from that. So you first want to find the area, and the area of question is this area. So that's what they mean, right? So obviously, what we look at now. What did happen? What happened here? Oh, let me just undo here. Yeah. So the whole beam itself is 250. Obviously, with this question, we just look at the 1/2 because this shape is symmetrical. We know that from here to here is 125, right? Okay. And if we subtract 50 from 125, we're left with 70. Are you guys all happy with that so far? Does it make sense? Right? Does it make sense, students? In terms of those distances there, right? So we're going to find the shear stress at that particular location, the green one. So Mr. Green, right? The Namekian. Thank you, Mr. Ngwane. And what we're going to do now is we have to find the area. So normally find the area, and you get a mark for getting the right area. So that's going to be a 0. So this is a 0.75, 75, yeah, obviously. So 0.075 times 0.1. So that's the area you must focus on, right? 50 millimeters away from the neutral axis. So that's going to be, can someone give me that area? So 0.075 times 0.1. That's what I'm looking for. Come on, students. Yeah, okay, 0.0075. Thank you. 0.0075 meters cubed. Now, a y bar is going to be the y bar from here. Let me just use another color, maybe. No, it's not a smart color. Something more lighter. Maybe this. A y bar is from the center from this to that over there. So if I look at that, we're going to have to say our y bar is going to be 50 plus 75 divided by 2. And here you get 50 plus, what is half of 75? So we're going to have to take 50 plus the half of that, whatever that is. So that's all written there, I think. Let's just work it out. So we take it to the center of that particular location. So that's very important for you to understand. That's why like I said, I'm doing it. I said it's 50 plus 75 divided by 2, right? And I get 87.5. So I get my y bar is 87.5. Okay. Right. So if you get this right, you probably get a mark here and you get a mark here. And then to find your shear stress at AA, it's going to be your shear force there of 10 kilonewtons. A is 0.075, 0075. I mean, I need to program my graphics tablet again. Y bar is 0.0875. I beam, it stays constant, which will be the 130.28 times B, and B is 0.1. So B is this counterpart for this approach, it stays constant, right? And so we can get AA. But you're going to find the magnitudes are normally very small, and that is why they have somewhat negligible effect on the beam. So you appreciate once you start getting into the bigger stuff why this is important. Last year, challenging time last year. So what is that shear stress in section AA? Can someone give that to me? Hello. Are you guys present? Who's mine in havoc? And Elisa, mornings. Good to see you here. 504. Thank you, Zach. Okay, 504 kilopascals. Beautiful. Right. This is well within 1, 2, 3, 4 marks. Okay. So what I want you guys to do now for me is quickly compute the shears in section BB, and BB is 100 millimeters away from the neutral axis, right? So that's BB. Just a quick exercise to warm you up. Thank you, Mr. Kiefer. Yeah, that's a lot better. So can you see small magnitudes, right? Doesn't affect much in the beam. It's not within the 200, 300 range. Megapascal, this is kPa. So very small effect. So let's just do another warm up of 100 and see. Are we getting there? So we're doing good, we're doing good. So what is the area, what is the Y bar, and what is your shear? Y do times it's B. It's the breadth of the section. IB. That there. IB. This bottom part stays constant. Yeah. Just Q which is changing. There is other ways of doing this thing. It's like yeah. But anyway, see the adopted approach here. Okay. So another section with arguably 3 marks. Just have to know the procedure. That's basically all. So if you know the procedure, you cannot not fail this thing. Yeah, but you know, anything happens with you guys. So for this one, if we're 100 millimeters away now, the area in question is going to be this over here, right? And obviously that's still going to be 100. That's going to be now 25. So that's your new area. So it's 100 times 25, whatever that is there. Obviously it's in millimeters squared. Yeah. Mr. Keeper, can I ask you, how do I know that answer is correct? How do we know that answer is correct?
Because I gave it to you, sir.
Yes, for sure. Yeah.
I don't know. Give me a second to think about it. It will be proportional to the first answer we get, because it's all on that same triangle. So there's some proportional on the left, on the left on the equal sign is equal to what's on the right on the equal sign.
Yeah. So I think what I want to say is decreasing. Remember, so there's no shear force there, and it starts basically decreasing as it's going up. We're actually going up along the beam here. Doesn't make sense. So the maximum will be here. But obviously it is proportional with that shape. But the shape is a parabolic shape, by the way. But yeah, I'm happy with this answer. There's 216. So it's 216 kilopascals, right? So if you there's a small exercise like this which continues along the length of the beam. I think that's what we'll be doing. Okay, so I'm quite happy with that. So if you're able to understand that concept, especially with the areas, that's a good thing. And then touching on the next example, which I'll just move along here. It's also from the website, so I highly recommend you checking the website out. Really, it's like, I mean, when I just found it last night, you know, like it's one of those things like you're so glad it's just breaking down these concepts for me. And in this case, it's the same beam, and we need to obviously find it at the neutral axis. And it's the same exercise as before, but when we find at the neutral axis, we consider the whole area. So let me just lock that. Right? It's the same amount of force, everything. It's the same example. So we just find the whole area. So to find the maximum one, we know the area now. It's going to be 0.1 times 0.125. So that's the whole area here. You get that answer. Your y bar, which is the whole area, it's just basically 0.125 divided by 2, which will obviously give you 0.0625. And your maximum shear stress will be 10 kilonewtons, right? Which is given in this case, for this example. You've got your area 0.1 times 0.125 times 0.0625 and divide that by IB. And IB was 103.208 times 0.1. Okay, you guys got that? So what is my maximum shear stress there? The answer is on the website. Share with you guys. What do you guys get? You should have got this answer. Okay, where is it? I'll just better check your guys' answers, but here's the answer for it. Boom. Skipper got it. Yeah, Jason got it. Fantastic. 0.6. So that would be the maximum, and obviously decreases until the top of the beam, and the shear force on top of the beam is 0. So here I will ask you, the top of the beam, the shear force is 0. The top and the bottom part here. Shear forces here. Obviously, there's no shear forces if you think about it. Because I mean, this is the cross section, the beam is shearing across that area, and it's over here. There is no area to shear. So you must think of the force acting like this. Yeah, I don't know, maybe I should have it like this. And then force is acting here or something. Okay, cool. Right. We can move along. So guys, are there any questions? What's important is the so-called Q, the I times R. It's the first moment of everything. It is the first moment of area. Are we all happy with this? Is there any questions before we move on? Any questions, students? Thank you, Mr. Hermanus. So like I said, your rectangular beam and your I-beam is the beams in question. Maybe a T-beam, but I highly doubt it.
Sir,
So I want you guys to, yes.
on the shear stress here,
Mm.
I'm seeing down there 0.8. Is that
No, 0.1, sorry, man.
okay?
I don't know why I'm scribbling. Yeah, that stays constant. Yeah. Okay, thank you. Yeah, I should get, I'm not sure the exact answer. All right. So, we're nearly done with the first half of the session. Well, is it the first half? Well, there's 3 parts, I think, of the session, if I'm thinking about it. Okay. So if you have that concept, well done. And we're moving on, right? So, obviously, I want to give you enough practice while we are here. And this was the actual first example I planned for you guys. But obviously, I found the websites. I thought this is fantastic. So this is what a question might look like, for instance, where I give you a beam, and I did mention to you, right? And from the beam, you have to work out the shear force, right? And then obviously from that, once you have your maximum shear force, that is the shear force you'll be using and to calculate stress distribution. So in this case, you want to work out the shear stress at 0, which is on top of the beam. Oh, yeah, so 0, which is 0 millimeters from the neutral axis, which is at the neutral axis, 40 away from the neutral axis, 80, and then 120 above the neutral axis. This is like a common type of question, but normally the question will maybe just state find the stress distribution. Obviously, you have to find into the beam. So what I'm going to do is give you guys a moment, around 10 minutes, to get the shear force and try to work out one of 2 of these things. Where we're going to go to this afterwards. I'm glad I can actually do this in an exercise. Where we go to this afterwards is I'll prescribe some general formulas for it, talk about the circle. I'm going to skip this one, and we're going to go into the I section. Once we do the I section, we probably got 1 or 2 examples here. And after that, there's a T example, which I might not do. We're going to go into the bolting beam. So like I said, what's important is to know a rectangular beam and to know an I-beam in terms of its distribution. And this is multi-beams. This is a different animal on its own. It's not a big animal. It's used in combination with second moment of area. This is from your first class test, so we work out that I'll explain to you how it basically works. So yeah, you'll see. And you understand, once I go over the whole lecture, you understand, oh, okay, it's not that bad. It's really not that bad. But I want you to guys just to try this one. But always be conscious. This is the one I'm telling you now, and please pay attention. Please be able to draw your shear force and bending moment diagrams, right? The beams might not be that complicated, but please be sure you can draw it. It's very important. You're going to need to find your maximum bending moment, and you're going to need to find your maximum shear force, which you're going to use for other analysis. So I'm making you please aware those you might lose critical marks by not being able to do that. So that's why I'm giving you an example like this. So you're aware that you're going to get a beam, you can get any beam. And in the cross-section area will be maybe for the shear stress, for instance, a rectangular or an I-beam. There's only 2 you can get, and you need to conduct analysis. But this part will change, obviously. So I'll give you guys 10 minutes. Try to find at least from 0 to 40, and then I'll solve the rest, obviously, as I go along. And if you have time in between, you can check the notes I've posted on Blackboard. And yeah, anyway, so just have a quick go with this. I think this is a small exercise. A very good example as well. Easy, easy, easy. So see you guys in the next 10 minutes. Did you guys manage? Let's see. Okay. Mr. Kiefer has some answers. What are those answers actually? Let me have a look. 116, 185, and 208 and 0. Let me see. He's out. He's out. Probably got his shear force wrong. Okay. So let's just quickly do this. So let me just. Do I have it prepared on my whiteboard? Yeah. Okay. Oh. I think a shear force is probably wrong. That's what I speculate. Damn, I tried. Yeah. Yeah, it's long to try that. That's what's important.
What's the maximum shear force?
208. That occurs at 0 millimeters. That's at the neutral axis. Yeah. Maybe just close a lot of things open here. I'm just having a whiteboard. Won't take long.
I'm talking on the diagram.
Oh, the maximum shear force. Okay.
Yeah, it's
So
7.
the maximum, yeah. What's it?
7.
5.
-5. -5.
Minus 5.
Minus
Yeah.
5.
Yeah.
Okay.
Cool. That's where people are out. So if you look at the note there, so I'll just quickly show you. So your maximum shear force diagram should have looked like this. Yeah. So something like that, right? Obviously, I'm assuming everyone can find their actions here. It shouldn't be a problem. But the value you should take is the highest value, which occurs on the diagram over here. So I'm hoping you guys can do this. You got to first find the reactions, obviously, and then based from finding your reactions, you need to obviously find the shear force along the length of the beam. So they've used A, B, C, and D. Normally, it's obviously normally guided for you over there. So just be very aware of being able to find that. Mr. Kiefer, was your shear force correct?
No, it was horribly wrong, but I forgot that we had to start at the left-hand point and plus and minus everything. I got 11. I got 11, so I just added everything going down. So I thought, okay, what's going down is going up, so that must be shear force.
Yeah. So I've picked up that tends to destroy a lot of students. So I'm making a way, make sure you're able to do that. Okay, cool. So once you have your maximum force, it's going to be on your diagram, and your Vmax will be in that case 5 kilonewtons. So obviously, if you have this, you'll probably get a few marks for that, 2 or 3 marks depending. And so what we want is just basically find this test distribution here, right? So we've got a beam, a rectangular one, and FB, FD, so I don't VAD. In this case, is 150 wide and 240, right? Okay, so obviously we know our maximum on neutral axis will be half here, so that will be around 120. So we normally always work with half the beam anyway. So instead of me starting at 0, I'm going to start off 120 above the neutral axis and then move going the other way. So 120 above the neutral axis, I should just actually move this. Yeah, it's obviously there, right? And at this particular point, so the shear at 120 millimeters above neutral is 0 MPa. There's no shear force over there. So what I'll do now is move to my shear force at 80, right? And obviously we're expecting it to increase until the so-called maximum over here. So remember our formula is V A Y bar over I B. Okay, so from this we have to calculate our I anyway. That's always going to be IXX. So that's 0.15 times, this will stay constant along the length of the beam over for this kind of thing, not constant along the length of the beam, but yeah, for the whole beam. So 24, right? Cubed divided by 12. Let's get our answer there. And you should have gotten 172.8 times 10 negative 6 meters 4. So you should have gotten it. Now obviously the AY is the so-called tricky part. So in this case we are 80 above, right? So if you're 80 above, okay, I don't know how should I get this here. So let me, yeah. That means if you're 80 above, let's say it's 80. That means this will be 40 over here. No, yep, 40. Okay, so we know that our area, so I'll just write this here, shear at 80 millimeters is going to be your 5. So you can obviously see this is where the first part the work comes. 5 kilonewtons. That area is going to be now 40 times the width, right? 40 times the 150. That's very important. You make a mistake with the areas out. So it's 0.04 times 0.15. And obviously now we just need a Y bar. And a Y bar is obviously going to be 80 plus 20, which is 0.1. So I'll just have here 80 plus 0.2, sorry, which is halfway. And then I is 172.8 times 10 to the negative 6 times B, and B stays constant at 0.15. Okay, so let's get my shear at 80. Someone give me the answer. I hope I did it right. So we're just going to do it until the neutral axis, obviously, and then. But it's a good demonstration of what you can somewhat expect, especially with the area stuff. You'll see. Okay, so we're gonna move nice and fast after this. Yeah, so let me just quickly see. 100 and yeah, that's fine. That's perfect. 11574. Yeah, 115.74. Once again, you can see how small it is. Very small, very small. Okay. The next one. So the shear at what's the other one again? Where are we now? Yeah, at 40, right? 40 millimeters. And so obviously I'm not gonna still. Obviously you wanna sketch your thing. So if I have a look at my let me just resketch it. Let me just be accurate. Again, your beam, neutral axis. No, what happened here? So this is going to be 120. So we're 40 above, right? So we're 40 above. Oh man, what's going on here? So we're 40 above. We have 125 here, and we have 80 in this case now. Because obviously this is 120. We know that this is 120. So it's maximum shear force stays the same. And the area is now 0. Why am I saying 1, 2? That's 0.15. 0.15 times what's this? 0.08. So that's, like I said, that's the key. And in the Y bar, obviously it's going to be 40 plus 40. I hope you guys can see that. I think that's right. It's 40 plus 40, all the way there. And then 172.8 times. Okay. So don't worry when you go full steam. I realize I'm trying to my best to make it concept is this lekker solid. Yeah, 185.2. That's definitely the correct answer. 185.185. Okay, 185. Okay, so obviously don't have to still. I'm gonna have to do the next one. You guys can sit and do that. And obviously, when you're at the neutral axis, don't spend too much time there. You do exactly the same thing. But remember, the neutral axis, you're considering the whole area, and your Y bar will be at 60 millimeters, right? Obviously, this is 120. So always remember you're working with half the beam, and that is, and you're gonna find it across specific distances. So it's quite easy. I think that when I started like this, it makes it a bit more easier. You know, the I-beam obviously has its own peculiarities, which you obviously have to prepare for. Okay. So now, I'm gonna head back to my slides. So is there any questions before I move on? And you have the answers to this. There is a note for it, so that's what I said. So don't worry. We're sure you go over it. Any questions, guys, before I move on? Yeah, that's the max, yeah. Oh, I mean, obviously, sorry, I didn't mention, you have to sketch the distribution. Obviously, distribution will be something like that, yeah. So I don't want to, I don't know, waste time and things I know you guys can do. So, yeah, I don't look like this. Obviously, you have the solution so you can figure that out. There's no tricks, you just have to know, yeah. It's very procedural. Okay. So, yeah, this is what you're expecting. You see, that's what the distribution looks like. And remember, I don't know, it's fine. I don't want to talk about that now. Just keep focused. Okay, thank you, Annalisa. So guys, we passed part 1 and we're heading off to part 2. Let me just end of part 1 first of this, and not to say too much. I'm just gonna share this thing now. Okay, so obviously we just did this one, and now where I want to take you guys is to this here. So sometimes, in fact, there's another note. Well, in the first note, they've basically shown you a shortcut version where you can find your maximum shear stress, and to find the mean shear stress, you take F or V divided by BH, so you can find your mean. And if you actually want to find your maximum shear stress, you times it by 1.5. So this is like the basic show that they already derived this here, and I think a parabola, no, parabola is 2/3 or something. So if you want to find your, you can do that using this formula. So if we take for the same beam V over BH, and get the mean, and it times it by 3/2, we should have gotten the same answer. Furthermore, obviously we're going to play around with that now just quickly. Furthermore, over here is a general formula, right, for your shear stress beam across a rectangular section only. These formulas will not be given to you, but if you do know them, fantastic. I'm showing it to you so that you have a way to check your work. And what it basically is if you have the shear force divided by 2I open bracket d squared is the depth, divided by 4, and y will basically be the distance away from the neutral axis. And if you have that, you can basically compute along the cross section of the beam, and you obviously can see it's squared, which tells you the shape is parabolic, right? So just using these quick equations, so I'll just quickly snip them for you. Okay, what's going on here? How much harder would it be if we for the graph. How much harder would it be if we found the equation for the graph and then use it to find it at any point? Yeah, this is like kind of the point where I'm going to now. You don't have to find the equation. I mean, it's kind of given to you for this particular section. So yeah, let me just. So I'm just gonna. It's gonna take us. I don't want to take long with it. I'll just show you, just demonstrate for you. Obviously, the first part of it, yeah. If you look at Trotsky, the chapter is quite small itself. So I just want to show you evidence that it works, because obviously the I-beam has its own set of stories, which obviously you have to kind of also remember there. So I'm just showing you the concept of, I'm using a rectangular beam and boring it up to a more difficult beam, or obviously a beam which. So yeah, let's quickly just corroborate our answers. So what we're just going to basically do is find this. We're going to find the maximum shear force. So it's 3/2 using this formula over here first. What's the mean? So it's 5 kilonewtons, I think, divided by pH, and B was 0. What is B again? 0.15, and then D is the entire depth. So the entire depth was how deep was the beam? 0.24. What answer do we get for the shear max? Can someone just work it out there for us? See the line to us and the math is right. 0.24. Is that oh, 0.28? Oh, thank you. Oh, what was the shear max again? Oh, we didn't work it out, eh? Oh, but it's there. Yeah, it's 208.33 kilopascals. Exactly the same if you found it. And then if you want to use your formula, obviously with experience you remember this. So I'm saying I'm not going to give this to you. You can have this formula and you can work it across the beam, right? So it's V over 2I d squared. So I just want to use one data point as so let's use 80 millimeters away from the neutral axis, right? At 80. So you have V, so it's 5 kilonewtons over 2. What is I again? I can't remember my I value. 172.8. And this is obviously the general formula, and D was 0.24 squared divided by 4. So why math is beautiful. We can have chain relationships. And we're going 0.08. And obviously we're expecting the same answer there. And what do we get? What was that now? Was the time was in 1 year. Okay. Morning, Silas. Mr. Modal, mornings. Sergio Melo Molares da Abril. Mornings. So what do we get for that shared 180? Do we get the same answer? Mr. Abril?
I'm just greeting too. Also.
Oh. So what's an answer, guys? Come on, man. I don't want to still end up doing something which is, you guys are all, is it the same answer as before? 100 and what? Yeah, beautiful, beautiful, beautiful. 115.74. No need to write that down. Okay. Okay. Guys, are there any questions, right? Because now I've built the foundation for what we're going to do now. So I want you to understand, you know, this is not a difficult chapter. It's small. Just didn't like the way Trotsky explains it. But like I said, if you understand it, it's literally 3 marks. You can sit with a good 15 marks for a question like this. Any questions before I move on? We're ending off part 1. No questions? Can I get like a few thumbs up before I proceed? What IY? I don't understand what it means. Okay. What is what?
So I'm asking there, what is your y there? It's squared. It's like 0.00 something. What is it?
0.08. Remember, y is a
Yeah.
distance. Like what I was trying to show you that's any distance away from the neutral axis. That is y is. So sorry for yeah. So you could have done it for each, you know, at any position, and you see the distribution across the beam. There's like a general formula which you're expected to know, and I'm not going to give it to you. Obviously, it's too easy. Otherwise, it's too easy then. Yeah. Okay. Can I get some more thumbs up? Only got one from Jason. Thank you. Okay. So moving on, it's just basically a continuation of what we are doing here, and we are just, so this is just also for a circle. Circle has its own max. You can have a look at that, but you might touch on the circle. It's very seldom, but be aware of the rectangular one. Yeah? So there is a one for a circle as well. Anyway, okay, this is an example. Don't worry about that one. So here we go into the I section, right? And we are doing something exactly similar. What's important to note is how the distribution looks, and yeah, and obviously maybe you have a bit of experience now, so that I've taught you, but it's kind of implicit that the flange is the top parts, and then the web is that middle section, right? And how you normally find this is we find in the upper flange, we find in the lower flange, also top of the web, we find it in the web, and we find it at the neutral axis. So that's how the typical distribution for this looks like, right? And that's what the standard procedure. So again, with the same thing, we have formulas as well, which basically which you can use for the, we have questions here. But I'm just telling you now already that the same way we have the formulas for the rectangular beam, there are general formulas, but what you must be cognizant of is that one works for the flange. You find the shear stress distribution within the flange. So for the upper edge of the flange, and what I mean there, obviously I'm speaking very in general now before we do an example, in the essence of you know, you guys obviously more mature and understand the concepts. That upper edge of the flange is there, lower edge of the flange is there. It's also titled the top of the web. Obviously this is the web. So you're explaining in this text, and you have that as well. That's no formula for it. So it nearly looks the same as the previous one, hence me doing it. And then you have for the lower edge of the flange, you have V over 8I, which is this over here. I think we can see that. Sorry. D squared minus D, and also you have the distribution within the web itself. All right. Obviously, I'll teach you from first principles. And you can also find the maximum shear stress, which is over here, which is equation 8.11, which is F over IB, BD squared minus D squared over 8, plus BD squared over 8. So big D obviously is the distance from the upper edge, and then small d will be there. So I'm making away the formulas before the time, before we actually do it. But obviously I'll show you the first principle method, which is obviously what you kind of want to know anyway. And you can use the other formulas as kind of backup to make sure that you're doing the right thing when you're solving these beams. So obviously this is like part 2. So the 2 beams you're going to be focusing on anyway. And obviously there's a few formulas here, but I mean, don't worry too much. It's just, that's why we can do the first principles. It's obviously a lot easier. So out of the same textbook, I've given you, there's another example we're going to do now, and that is for an I-beam, right? After this example, we're going to use the same approach and do the example that was initially the one in Trotsky. The Trotsky has an example there. So we're going to try with our newfound knowledge, and maybe treat that as an exercise rather, to solve that. So I'll show you this one, and I want to try and actually use this the same approach, obviously, with the Trotsky one. Very, very important, guys. Like I said, whatever we did there, whatever we did here, you need to know how to find the shear stress distribution within the beam. And the way the question is structured here is a very good way of how it can be asked. So either you're going to get a beam, you have to find the shear force yourself, you find the shear force. For instance, I had a question like at the end somewhere, like this. You find the maximum shear force, and then you have to sketch the distribution. You have to sketch the bending stress distribution, which is obviously easy. And also, I added an extra part where I said sketch the bending stress distribution with a 15 kilonewton load applied through the beam axis. You know, like a direct load. And obviously, you have your direct counterpart and a bending counterpart. So that is like, I don't know if it makes sense to you of how a question can be amalgamated into one. Is it clear, students? Before I move on, you see how it all works out, because then you use your maximum shear force for the same beam and the maximum bending stress from the second beam. Is it overwhelming, or do you guys follow what I'm saying? Is your guys' minds not here also? Students? Yeah, okay, great. So it's straightforward. I mean, if you know that, it should be okay. Just need some more practice. You know, for sure. I know it's the first time you guys are doing it. Yes, exactly. And also combining chapter 9. Yes, Amaka. Exactly that. And you'll see it in the next part. It combines the 3 chapters, talk to each other. And that's the point of this kind of thing. It's a very good level, good subject level. I'll just give me a moment. I just want to check something here. I'm on this website. I want to just make sure I'm going to do the right thing. Okay, so I'm going to get back and we can start our first I-beam example. Okay, so be aware there's also general formulas that I'm also making you aware of for the I-beam. So before we start, normally I told students to use the tables, but I realized we have radiuses and stuff within the beam, so it's not, I can't really use that. So before we start here, I'd like you just to find me the second moment of area before we start with this example. Just find the second moment of area for that one quickly. I just want to see something here. Let's see here. I use it differently. Yeah. Okay. Cool. So let me just prepare the example on the whiteboard. So try to just send you a few examples on this. Once you've mastered it, then yeah, it's basically over. Like I said, it's not too difficult. There's no tricks. It's very procedural. And yeah, it's just, if you don't know how to do it, I mean, really, it's not really on you. Okay, so I'm just, the only tricky part is like if you get a beam, like what beam do you get? And yeah, okay, cool. So let's do the I-beam quickly. I just saw another way of doing it. It's just very fascinating, actually. Okay, cool. So first thing is first, finding the second moment error. Obviously, we assume that remains constant through there. Again, this is also in that other text. Yeah, Mr. Manus, fantastic. I assume we all found that, and I don't want to waste too much time. Obviously, guys, I did touch on that. To find this, it's just you're taking the outside section over here, the 80 and 120, and subtracting this, right? You guys are all obviously matured now, so I can move a bit faster certain things. Right, so here the gave us a shear force, but always be cognizant. You're gonna have to find that through getting a beam, right? Just for the ease of sake of the example. So 5.52 times 10 to the negative 6. Are we all happy with this? Do we all get this value? Do we all get it? Also, this is also preparation for your test tool. Just gonna put it out like that, yeah. So top of the web, that's up. Let's find up. Yeah, let's try to find in all elements here. Okay. Okay, are we all happy with this value? I started basic in my title, yeah. Just trying to figure out something, yeah. No. Okay. Anyway, so guys, I wish I could give you a mark for the formula. That's how we start. IB, right? Okay. So now, for the first part of the question, they're saying the one on the top of the web, right? So I'm going to have my sketch here. So top of the web. So top of the web means here, right? It's here, okay? Neutral axis obviously is some here. It's always like it's halfway. It's halfway the beam. Just for each segment, you don't want to make the things too difficult here. So top of the web could also mean lower edge of flange, right? Lower edge of flange. Yeah. On the upper edge of the flange, that's the shear stress obviously is 0, right? And we can find it midway as well. But in this case, we are finding on the top of the web, right? So, yeah, anyway, I hope that's going to be correct. On the top of the web, yeah, let me just quickly see here. So they're asking at the top of the web. So it's a bit trickier. And you can understand why. But I'll explain to you. Okay. Yeah. So what they're saying is a bit weird here. Okay, but I'll explain to you now what I mean. Okay. So first things first. We want to find it there, and if you want to find it here, the area in question is obviously this guy. So I'll make that green. Let me just get my dimensions in here. So we've got our 80, I've got our 10, and what's half? Is that 60, right? The neutral axis, from what's half the beam? Yeah, 60. It looks like 60 to me. Okay. So guys, I want you to see if you're smart. So using the same approach as before, you have your area of the section you need to do. You have the Y bar. 60 is the total distance, guys, right? Looking your way here. Get the Y bar, and obviously get the what is this, and your breadth, and yeah. So let me see who can get the answer. It's all in your notes, so don't worry too much about it. I just want to see. I have a slight problem with the question, but anyway, it's fine. We'll talk about it. Okay, let's just get your area, your Y bar, and then your shear stress. Let's see. I'll give you guys around 2-3 minutes for that. Beautiful, beautiful, beautiful question. Beautiful question. Do it for both. Beautiful question. The man has genius level analysis. Do it for both if you're not sure, and that is where I'm heading into, obviously. $2.5. Yep, that's correct. 2.5. Well done. Well, let me get back here. Okay, so let me sort this out. So so-called top of the web, lower edge of the flange, and this is what we mean. So I'm gonna have another one here. So area is obviously 0.01 times 0.08, and our y bar obviously is 60 minus, is it 55, right? You guys agree with me? So it should be 55 millimeters. Y bar is 55, 0.055. And then we compute that, you got 25 kilonewtons. Area is 0.01 times 0.08, 0.055. I will remain constant, as we said, 5.52 times 10 to the negative 6. And then B is obviously going to be 0.01. And if you do that, you should get your answer of, what answer do you get for that? Is that the 2.49? No, but oh, the thickness. Sorry. Yes. That's not 0.01. I'm talking crap. The thickness we should use is the 8. We should use the 8. Yep. I don't know why sorry, it's 8 times 10 to the negative 3. So I didn't include the thickness there. So that's 8. So you get 2,49. Now, there's something which I need to resolve here, right? So you've gotten that, that's fantastic. So the shear stress decreases Young modulus assuming applied force. Does the shear stress decrease? Well, shear stress, we don't talk about Young's modulus. We should talk about the modulus of rigidity. And if you look at your equation over here, rigidity equals shear, and this is your shear strain. They are directly proportional. And if the force stays constant, I'm not really sure. I have to really look at what you're saying. Okay, so this is Now I just want to make sure, do you guys get that answer, or because I'm with concern, I'm not concerned really, man. Let me just quickly see here. What area did you get? And what area did you use? So it's 24 point, yeah, it's 24.9, right? Is that correct? That's the
Yeah, I
answer you
think
got for this one.
that should be right, because I think what I did, I used 0.08, so 80, so that would be the shear stress on the flange, not on the web.
Yeah, now you have a, so it's not incorrect. So how did you get it 2.49?
I don't know. I used my area was
Yes, go for it.
0.01 time.
Yep.
It's basically 10 times 80, man. 10
10
times
times 80.
Yeah.
Yeah.
And then your
And your
I
Y bar?
times, and your Y bar was your I times 80.
I times 80.
Yeah, so 5.52 times 10 to the minus 6 times 0.08.
Your Y bar, I'm confused.
Oh, well,
just give
sorry.
me
Sorry. So Y bar was what's the name? 55 mil.
55. So
Yeah.
I think what I'm looking for here is, I want us to be aware of something here. The way they have done it, the answer is 24.9. That's correct. But I think I'll touch on it. I think later on, like more. What is this? What I'm looking for? I'll touch on it more as I go along. Get there. So I mean, I'm only going to do this one example anyway, so that's fine. Yeah, so you should get 24.9. Right, that is fine. Let me just unpack for you why. Just go to my slides. Why I'm like like I'm in between thoughts here. I'll show you now. It's no stress. Everything is perfectly fine, but the question does get there anyway. Okay, so this, like I said, this is a very test level question. You can literally get same question, different beam, and you have to compute all the same stuff. So I'm making you aware of that. That's basically all. No extra surprises. So what I'm making you aware of, this is how your distribution looks. You must know how to draw this. We found this value here. So that's 224.9 MPa. Now let me just get this right. Make this red, thicker. We found this guy, 24.9 megapascals. We have yet to find this guy here. So making you aware of that. And that is what I was trying to highlight, but I just remember the question itself brings out that. So now, for us to, before we get to the horizontal shear stress at the neutral axis, I want to quickly digress a bit. I hope I'm not going to confuse anyone. So just keep in mind, well done, you've got this. This is correct. I mean, like for instance, that is a mark, that is a mark. This is probably 2 marks. So you can see for the next part of the distribution is probably 4 marks as well. So before we're gonna talk to him, right? We're gonna just park him away quickly, and I want to go to my what is this that website I was talking about. Okay, so see, we are just so blessed and so lucky that we can find all these things to break up the concepts, because otherwise it becomes a bit weird. So we're gonna revert back to him. We sorted one part of it. So this is a classical case where another one, now to make you aware, this is now an I-beam, and we are required to find at section AA, all right? So what I'm going to drop you off with is the approach. So I'm going to put this in the slides as well. I'm going to see if you guys are smart enough to actually figure this out. That is what I'm looking for here, really. And the approach you're gonna have to take is this. So with the I-beam, if you're finding with a particular section, just give me a moment. And we're gonna go on a break after this, and then we'll conclude the lecture. Just letting you know. Yeah, so there you go. So when you're dealing with a section within the web itself, you're going to need to find the area of the first part, area 1, area 2, and that'll be your Q or your I, you know, your A and Y part. That is why they actually use Q. So you have two areas you have to work on basically with the area and your Y bar. So what I like you guys to do is try to do this one, obviously, and then we're going to do the next one together. But I want you guys to kind of figure out if you're able to do this. Yeah. Okay. And obviously the neutral axis will be essentially the same. The neutral axis area obviously will be the whole area itself. But anyway, so what you're looking for is section AA, and what you have to do now is where's your formula? Shear equals V I. So over here, what I'm making aware of, so luckily this all stays constant, right? Do we have a thickness? That's probably 10 mil. But this guy here will have two counterparts. Remember, this is like Q. So we have the first area and the second area. So to give you guys around 5 minutes, no, that's too much or too little, to try and figure that out quickly for me. And once we do that, then we can move on to the next part. So I'm just breaking down this piece here. So what I'm also teaching is, if I ask you find the shear force at 40 millimeters from the neutral axis in the web, you're able to do it, right? And obviously there is a general formula for you to play around with to see how the values work. So, but remember now for this, all I'm making you aware of, for an I-beam, we have two different areas, and this the first area, Y1, and we have to find the second area depending how far we are from the text. Okay, guys, so just try and find the shear stress for this guy. By 11:05, I'll step in and do this and continue the examples. I'm just breaking this further down. Okay, have a go. So I left the answers there somewhere. Let's see if we can You guys get the answers? Yep. Zach got it. Okay, let's have a look. So obviously, yeah, so I'm going to work out the AY counterpart. Obviously, all the rest is all easy. So what you're required to do is take the first area, and that's going to be 10. So I'm just going to have it like this. So it's, oh, so maybe I should actually write it over here. Okay. I mean, guys, I expect you to really get this. So I'm going to say A1 is going to be 0.1 times 0.01. And obviously, if this is the first area, you're taking it, the Y bar from there. So if this is 150, this would be 75. What would your Y bar be? Obviously, anyone else besides Zach now. Should be kind of obvious, right? So -5 maybe. So that's going to be, obviously this is 75, and then just -5, right, which will be 70, which will be halfway here. Okay, that's the first one. So I should have just called this AY-Y11. Plus, what we have to do is A2Y2 will be the second area, which is this piece over here, right? Second area is over here. In that case, let me just have a look. 150, 10 and 10. That is that's 130. So what is this distance from here to here? Checking in the chat here. What do you guys get?
35.
30? 35. 35.
Yes, sir.
35. No, I'm saying from this whole piece here. This call me 35. This you say this piece here. That's 35. Oh, you're saying that's 35, right?
Yes, sir.
I'm not sure. Okay. And obviously your thickness is 10. So let me just make sure. Yep. 0.01 times 0.035. And that must also be times your Y bar, obviously. So in this case, it must be over here. Okay, cool. So if this is going to be 30, and that isn't a 30 plus 35. So what is the Y bar in that case there? What did you guys get? $30 plus. I think your Y bar should be 47.5. Yep, thank you, Annalisa. Beautiful. That should be 47.5. Okay, so I'm not sure what this actually gives you. Okay, so if you've gotten that, so what it should look like is this. Shear equals 25 kilonewtons times 0.1 times 0.01 times 0.07 plus all of the others here, 0.01 times 0.035 times 0.47. That is your Q, so to say, or your AY total, and you divide that by, you're going to divide this by I is 1.16 times 10 to the -4, -12, I'm not sure, this -5 maybe. I think 1.16, and your thickness would be obviously it's because it's within the web itself, so that's going to be it's going to be 10 millimeters, which is going to be 0.01. Okay, and if you get that, you should have gotten the answer of 18.67 or something megapascals. You guys mentioned that. So what I'm just highlighting is finding this part over here. Okay. You guys mentioned that. I think Annelisa's probably got it. Any questions on that, guys, before we move on? Back to our normal example. So what I'm making you aware is when you're working with any section within the web, that's your approach going to be. You're going to have to take two areas now. Any questions, students? Mr. Kiefer, Annelisa?
Yeah, I looked away for a second and I see you did it differently to what I did.
Okay, what answer did you get though?
No, I
Thank you
got
for-
this, the 18.669
No, that's
megapascal,
perfect. Yeah.
but I got the resultant bar
Hey, why?
Y,
Yeah, yes.
because
You
I
can also
did
do that.
area moments to get one
Yeah.
bar Y.
Yeah, you can do that as well. Yeah, that is definitely correct. Yeah, that's acceptable. Okay. Thank you, Annelise, for responding. Alex, Aaron, Mr. Pereira. Okay, great, guys. So then just reverting back to our previous example, now that you have more experience, we need to just find it at the neutral axis. So this is B. And guys, like I said, you cannot I'll be disappointed if you guys cannot find this distribution, especially in the second test. So here I'll be at the neutral axis. And like Mr. Kiefer, you can find a common Y bar. That's what they do as well. Or we can find it shape by shape. You can actually find you can. There's two ways of doing this. Maybe we should do the other way. Yeah. So let me just get my dimensions. This is 10. This is 80. And that's going to be 8. So obviously we have to separate it into areas. This is going to be the one area, and this is the second one. So the way Mr. Kiefer did it, and this is also in your note basically. So what you can do here for this one, the area total will be 10 times 80 plus, you can do it either or. What is this length again here? Is it 50, right? And that's 8 times 50. Okay. So we're going to find Mr. Kiefer's way of doing the total Y bar instead of finding the individual ones. It's really the same thing. Hopefully it's not going to confuse you guys. Let me just quickly see. Let's say, so it's 5 times 8. And the area should be 1.2 times 10 to the negative 3 meters cubed. Okay. And if you're finding the Y bar, you can find a total Y bar like you said. And that's basically the same as you know the other approach where we're just going to say the first area is 80 times 10. And then what is my Y bar from there? It's from there to there. Is this 50 here? I'll just get this right. So 80 times 10, and that's 55, I think. And for the second one, it's going to be 8 times 50. And obviously, that's 50. I think that's going to be 25. See, someone said something there. 30.7. Is that correct? Yeah, I hope so. Yeah, that is definitely correct. Yeah. So that's the other way of doing it. Where was I now? Yeah, that answer is correct. So I'm looking for that Y bar, and so it's going to be, I'm just getting my distance in 25, right? Okay, cool. So if you divide that by, and of course that's the total area of 1.2 times 10 to the negative 3. So can someone just give me that Y bar of that two shapes? Then your shear is going to be this is at the neutral axis. at 25 kilonewtons, your total area is 1.2. I'm just waiting for that Y bar there. So you can do it two ways. You can do it the way I did it, or you can just do it like this. Maybe this way is a bit better. I normally use that way anyway. And your I, we've worked out, Mr. Minus worked it out to 5.5. So you can find a central axis of this particular thing, and then just use that to the total area. It's 5.52, and then obviously we're within the flange, and that's going to be 8. So you guys can do this, fantastic. Okay, we're moving on quite nicely. I can speed up now. Okay, so what is it, Y bar over there? Let's get my Casio open here. It's 80 times 10 times 55 plus 8. Guys, are there any questions? Are you following what I'm doing? I know you should be following. I know no one should be lost. I think is it 45 millimeters, that Y bar? That's 45 millimeters. I just use my Casio. So that's 45 millimeters. So it's somewhere. This is 50. So it's somewhere there. Yeah. So it's 45 millimeters. So that's 0.045, and then your stress will be 30. What did we get, Mr. Romanus? 30.57 megapascals. Obviously, depending where you are, you're gonna have to check. Guys, are there any questions before I move on to the next part? B. Oh, we're not at B yet. At number 2. No questions? Okay. So when you go to B, why are you guys so quiet today? Is it because of NAVOC? Are you tired? So B says, what is the shear stress in the web? Assuming the web carries the whole of the shear force uniformly distributed over. Okay, someone say something. Stressed. Yeah, don't stress, man. Just focus on the work. Don't make things too complicated. I'm the one who's actually stressed. What is the shear stress in the web, assuming the web carries the whole of the shear force? So while that's normally not the whole of the shear force, but that's normally the case. Let's just quickly look. Just to complete the distribution, where is my note here? So what they're basically just working out here is we've obviously found the maximum shear stress within the web, and what they're referring to is that all you have to do is now say shear V BD, and this is going to be in the web, and you're going to see how close it is. It's just like an approximation kind of setup. What is the shear stress in the web, assuming it's just like kind of carrying it over. And let's have a look quickly. And what is V? V is 25 kilonewtons. And B was 5. It was it's the web. It's 8 millimeters, which is the breadth. I don't know if Mr. Manus posted something there. And then obviously the depth is going to be just 100, I think, to 0.1. And if you work that out, you should get an answer. So let me just clear my calculator here. And the point of this is just to show if you use an average value. What answer do you get for that? 31.25, right? I wonder if that's the correct answer. Yeah, you get 31.25. Okay. So what you're just saying is that if you just assume over the mean area And if you compare those two values, it's roughly the same. I can't tell exactly in terms of percent, but obviously this is the more accurate approach over here. So 31.25 megapascals. Now this is my favorite question, and we're heading there now. And it says, what percentage of the total shear force is carried by the web? One of my favorite questions. And we're not going to use integration to do this. We can use integration. And we're just going to find it using our analytical stuff, right? Okay. So what we're required to do now is find the shear stress at, so I'll show you exactly.
You have to divide the shear stress from the flange by the web.
Yes, basically, yeah, across the web. So we need to find the shear stress at this particular point. I didn't mention to you. Yeah, let me just quickly show you. Oh, I'm in the wrong place. I can actually just talk to it here instead of working it out. So at this particular junction over here, right? There. So I'll just go to the note and show you, because I don't want to spend too much time on showing you this. But yeah, if you can do this, it's not that difficult actually. Okay, so I'll just copy the solution over here. Okay, so what you're required to basically do, and what one must be cognizant of here, is you need to find we need to just find the shear stress within the flange itself. That's the first thing, right? And the only difference between our previous equation, this one over here, where was it one? The first one that we did, this one over here, you can see they said your instead of 8 millimeters, we're gonna have to use 80 millimeters at your breadth, right? So if you just basically, yeah. So then what they're talking about here, hold on, my bad. So we're just basically finding this point over here, and here last time we used, remember over here for on top here, by the way, on top of the web we used, remember, 8 millimeters, and now we're obviously just using 80, which is going to be obviously it's within the actual flange. And we have to find basically the stresses on top and the bottom of the flange. And yeah, obviously on top it's 0, like I've mentioned, and 2.49. So what they say there, we have to find the average shear stress across the flange, and that's quite easy. I think that Alex was referring to. To be honest, this is, you guys can obviously figure this out. This is not difficult. You divide that by 2, and you get 1.25 megapascals, right? What you then do is then to find the shear force, which is V, it's going to be that stress, right, times the area of the actual flange. Okay, 0.08 times 0.01, that's the area of the actual flange itself, and you're timesing it by 2 because there's 2 flanges on the top, right, and you get 2 kilonewtons, right? Once you have that, obviously you have the maximum shear force, and the maximum shear force was given to you as 25 kilonewtons, right? Let me just quickly check something. I'm just having a look here. 20. Okay, cool. Let's see the more easier way to do it. So we know V max was 25, so we're just going to say 25 minus V max is 25, and then if you want to see how much the web is carrying, I'm sorry, the flanges. So we found the shear stress within the flanges, right? We had the maximum shear force. So if you want to find V web will obviously carry 25 minus 2, so that's V flange over here. Okay. And then V web will carry 23 kilonewtons, right? So we found the flange already carry 2 kilonewtons. Obviously, if you look at the diagram over there, you can see that makes sense. It only carries a little. Remember, it carries mostly the bending stress on the flanges. And then the web, you found the web's load, and then all we have to do is the percentage shear force, And like these are all the extra good bonus marks. That's how I'm making you aware. So 23 divided by 25, which will be the total. It's just a percentage thing basically, yeah. And you end up with 92%. So again, I'll just recap. All you're basically doing is finding the stresses on the flanges. You find the force basically within the flange, which is 2 kilonewtons, and you're subtracting that from the maximum 25 to get a 23, and that 23 will be the web. Remember the web in this case carries most of the shear force, and then divided by 92. There is another approach we could have done, and that's with integration. So yeah, and Trotsky is that. Is there any question to that? I don't want to spend too much time on something you can actually like play around with and figure out. It's clear, students. Was my explanation at least clear?
So
that's what I'm looking for. Yes, go for it.
if you were to rotate that I-beam like 90 degrees, right?
90,
so it's like instead of you see it standing vertical, it's horizontal.
Yeah.
Then how do you find out what the percentage of the web is carrying? Because now the flanges will be taking all the load.
Yeah, but then you just shouldn't you be doing all the same stuff then? I mean, isn't the errors going to change?
So nothing's gonna change. Yeah.
Yeah. And also like I'll never give you something like that, for instance, just by the way, if you are worried. Yeah. The I-beam will always stand like that because that's how I-beams are designed. But if this is the case, you load it up like that, then obviously it's inverse to this. Therefore, this part is going to carry most of the thing. You just have to kind of work it backwards. If you have time, you can actually do it and let me know.
Okay.
Yeah. Obviously, it's we're not running for. It's not time to experiment here anyway. So I was going to show you Trotsky. They do show another approach in solving something similar to that. So what I'm just making you aware is that guys focus on this question, know the procedure, you just get a different beam, and yeah, the other alternative on how to find the what you call it, to find if you want to find how much the web is carrying, you can also use integration, which we'll be using anyway in the next chapter. So there is an alternative approach. So the reason why this approach is there is to basically show you, it shows you, what is this now? It basically shows you, yeah, it's obviously more, it's more like, okay, it's arguably algebraic and this is more these integration. They're both, yeah, but anyway, yeah, so same thing. Just make sure you understand the procedure of how to solve. It's always going to be the same, literally all the same. Okay. We can actually just repeat that example. So guys, this is end of part 2. I was thinking of we do electrodes on Wednesday rather at 9, if you guys don't mind. Or we can always do electrodes now again.
I know that's lucky for me, so because I wouldn't be able to attend electrodes this afternoon. I have to go check on my baby.
Oh yes, well yes. Okay, so we'll take a break and then I want to finish up this chapter in strengths, man. But what I'm saying to you guys, please know how to do a rectangular beam. Please know how to do an I-beam. It's a procedural thing you need to do here. And this is the end of part 2. And basically, we'll take a extended break, go into electrodes, and finish off. So we have like an hour or so left, and then we'll be done with stresses. Not a difficult chapter. Please do not make it difficult. There's no tricks involved. I'm telling you now. Make sure you go over the work. Because I get very hurt when I see my students fail. It really makes me wonder, what are you listening to? But anyway, furthermore, with the same stuff I did mention to you, here are some formulas. You can use them. I'm not going to give it to you. So make sure you play around with them. Right? So I've delineated for you. Make sure you know your rectangular beam. Make sure you know your I-beam. And what we're going to do in the next session is basically bolt-up beams, which is it's going to be nice and quick. Hopefully we can just do 2 examples. So the one is going to be your first class test solution. Your second one area, which some people couldn't even get, shockingly. And then we're going to include the second part of the question on basically you know, where the new part is, or the shear testing. So it's very easy actually. Just a few things you must be aware of. I've got a few questions I've posted on Blackboard, which looks like that. Some test level type questions anyway. Again, what I'm making you aware of, I'm going to say this again. You're going to get some I section like that. You're going to get a beam. You got to work out the shear force. And then you got to use the procedure I've taught you to analyze that. Is it all clear to you guys? There's no tricks. The only trick is changing the beam. I can change the beam to whatever I want. So I don't want people to fail. So I'm telling you guys, make sure you master this thing very well. Make sure you know the procedure. Obviously, you have to sketch the distribution, and the nice bonus marks will obviously be calculate the percentage shear force within the actual thing. So I think what I want to leave you with now, before we come back to the last part of strengths, is because obviously you guys have nav walk, so I want to finish around. I don't know how long we should have a break. It's a key 47 minutes. Just a quick break, extended break, and we can just finish up before your nav walk periods. And obviously you guys have nav walk on your mind. What I want you to do now is for Trotsky example 1, right? Use the shear force approach. This approach I taught you now. Where's the approach now? Where's my whiteboard now? Let me go find my whiteboard. Find the percentage shear and just post it in the group for me to see if you can manage. So using this approach over here. So, man. Anyway, just forgive me. This approach here, it's example 11.3, and try to see if you can get this. Obviously, you need to work out just the inner part of the flange there. The answer is actually there if you look at it. So use this approach to do example 11.3. Is it clear to you guys? This part is the bonus marks. This is for the men and the women. But if you can do it, fantastic. You got your marks. And always just know that the most of the shear force is carried by the web. Obviously, if you're doing something wrong there, it's a problem. All right? Is it clear, guys? Mr. Kiefer? How long should we have a break and then come back? Thank you, Mr. Demanis. I don't know if it's an old, no, it's an old one here. Well, it's a new one here. So please just do that quickly, and I think as long as you finish up to 13:20. Yeah, so you can just, maybe we can have like a 20-minute break and then come back and then just finish up. The last part is going to be quick. It shouldn't take me more than an hour. So if we come back at 12:30, I don't want to take an hour. So let's say 20 past. Yeah, then we just, as long as we're done by 13:20. Yeah, okay. Yeah, so let's come back at 12:20 and then finish up by 13:20. Trotsky is a bit it's a bit limiting in its way. Obviously practice those examples, but I have posted enough extra stuff for you to do. Okay, so what I like to do just now, but okay, no must ask what? But then no must ask questions. Yeah, no, it's gonna be quick, man. Don't worry. You'll see. Yeah, this is a short section as you see, but I've tried to make it as lick as possible. But just please, I would like to see you guys. No one must ask questions. Yeah, does take time. I'll also myself, but anyway. After this, I'm gonna post. I'm gonna put in the marks and stuff on my spreadsheet, and then I'm going to upload the class test. That's my next task after this. Yeah. Anyway. So after we're done the lecture, so you get that during the course of the day. So let's just use this approach. It should be within your notes. Please do it. I can obviously do it. I'm gonna do it now myself. And yeah, so this is the end of part 2. And then part 3 is just bolting beams, finding the rivets, and the welded connections. Not difficult. Involves a bit of second moment of area, and there's some few extra stuff. And then you're basically done. Okay, guys, see you at 20 past.
Sir,
Yes.
we're not having electros.
No, we're gonna have it on Wednesday,
On
9
Wednesday.
o'clock.
All right.
Yeah, I just want to finish this, Mr. Matoso, like, this one chapter out of the way, instead of coming back again and then, just getting it done.
It's cool.
Yeah, thank you. So we can just put it behind us, and then we can move on to deflection of beams next week. Yeah.
So you'll obviously be recording the next session because unfortunately I won't be here. I need to go to the hospital.
Yeah, it's fine. Yeah.
Okay, shot.
Yeah. But it's you'll see it's always recorded. It's easy. It's not difficult. The next two sections, I don't want to be problems, guys. Your next test needs to be very good. Some of you guys have suffered drastically. So yeah. Anyway, guys, I'm gonna do that quickly, and then I'll see you at 20 past. Go stretch your legs, go have a coffee, and then we'll finish up shear stresses. Okay, cheers. See you 20.